Everyone. So in this talk, I'm going to be talking about Apache Hudi, an open source software to build your Lakehouse platform, and how that integrates with query engines such as Presto and Trino. Um, uh, I'm currently a software engineer at Onehouse and actively contribute to Apache Hudi, Presto Trino projects. Prior, I have been an engineer at AWS, worked on their Amazon Aurora, and I started my career as an MTS at Oracle, worked on Golden Gate. I'm not sure how many of you have heard, that was a heterogeneous database replication software. So this talk, our agenda will be, first we'll start with Lakehouse architecture. The architecture has seen phenomenal growth in this decade at least, and then we'll see, okay, everything is not rosy with Lakehouse architecture. There are some challenges with the architecture as well. And what kind of solutions does Hudi provide? What other solutions are there? Open source solutions are there? And how Hudi works with Presto and Trino to enable fast queries over your data lying on Lakehouse. And finally, we'll just wrap up with Hudi as the Lakehouse platform. So the Lakehouse architecture, right? So it's just a fancy term. I think Databricks folks merged data lake and warehouse and called it Lakehouse. But essentially, it's a transactional data lake. The kind of transactional features that you get with databases, that's what Lakehouse architecture tries to bring that directly on top of your data lake. So I think with the advent of cloud computing, decoupled storage compute was one of the best things to have ever happened. But Hudi or in other formats that we see in Lakehouse architecture like Delta Lake or Apache Iceberg, we also go beyond and see if we can make it engine agnostic. By engine agnostic, I mean compute engine agnostic. Like, can we write using Spark and Flink and read that data through Presto Trino? So yes, you can do that. And Hudi was kind of first system which introduced this concept of copy on write and merge on read tables on data lake. You could do change data capture on lakes. And those ideas were now heavily borrowed by Databricks Delta Lake as well as Apache Iceberg. So Hudi was born at Uber. It was open sourced in March 2017. But first of all, I want to go back to basics. This is from a seminal paper. This is the architecture of a database system. I don't want to talk about lakes and Lakehouse right now. Like, what does a database, essentially, what are the components of the database, right? You have a client, and then on this side, you have some background activities happening that database provides. But the core of the database is about this block down below, the transactional storage manager, and this block, right? Query parsing, query optimization, query planning. So what Hudi attempts to do is be this part for your Lakehouse, the transactional storage manager for your Lakehouse. And we'll see in a minute how it attempts to do so. It tries to be engine agnostic. So for your query optimization, you can still leverage the plans generated by, let's say, Presto or Trino or Spark. You can use Spark SQL to query your data. It builds, in short, it builds a very thin database kernel on top of your data sitting in object storage systems or HDFS. So yeah. This is a very beautiful diagram which summarizes the evolution of data architecture. And this is from the Lakehouse paper, which I've linked here from Databricks. So first generation platforms, they started with, you need to have that structured data coming in from transactional databases. You do some ETL, then load that data into data warehouse. Data warehouse add their own set of metadata, and then you could generate your, you could run your BI queries, generate reports, analytical queries, right? And then it evolved into this two-tier architecture when the machine learning data science use cases became more and more prominent. It was no longer easy to structure the data beforehand. So structured data would sit along with your semi-structured, unstructured data on Lake. Lake is nothing but your, either it's a block storage system like HDFS or object storage system like S3. And then that's Lambda architecture evolved where you would sort of still do ETL to load the data into the warehouse, where you can generate reports with much better consistency guarantees. But for machine learning, data science use case, maybe you can just scan the data lying directly on your data lake, right? So this was, people ask questions like, why do we have to maintain two different tiers? And it became a maintenance overhead. Maintenance overhead aside, there was also freshness, liveness issues. So that's when Lakehouse platforms, and still very new. I mean, most of the companies are still on this two-tier architecture. What Lakehouse platforms do, they will, going back to that database thing. Okay, yeah. So the storage manager, right? So something like that, Lakehouse platforms will build a very thin metadata caching indexing layer on top of your data lake. And using this, all different use cases can be sufficed. And we'll see in a minute what Hudi does specifically for this part. So I talked about Hudi's copy on write and merge on read tables. But what are these? So first of all, how does your data come in? I think the most common format that people use for analytical queries, it's a columnar format. Either you're using Parquet or Orc. And let's say you have some raw data, raw Parquet files here. File 1, T0, it has records A, B. Another file 2 has records C, D, and E. After some time, you ingested this at commit time 0. After some time, you are now getting some updates for record A and D. So copy on write table, the concept behind that is you're going to copy the existing thing while writing and get the updated data, put the updated data into the copied file, right? Subsequently, a background process will go ahead and clean the older data, older versions. But essentially, yeah, you are doing whole copy while writing the table. So this has some write overhead, but the good thing about this is, while you are querying the data, so you just need to load the snapshot of the data at that particular commit time. You don't have to go back and look at what was the base record. And okay, it will be more clear when we look at merge on read table. So everything in a data system revolves around this read-write trade-off. So merge on read table, same thing. You start with a base snapshot. You ingested at commit time 0. At commit time 1, you received an update for A and D. What you're doing here, instead of copying the whole data, you're just writing a log. And then you are saying to the client, I'm done, I've committed, right? Just the update is getting written to a log file. Similarly, at commit time 2, you received another update, a new insert, and Hudi will intelligently try to figure out, okay, this new insert, to which file should it go? But it will again generate a new version of the base data. This is again a log file, and so on at commit time 3, right? Now, comparing that to copy on write. So copy on write, you did have some overhead while writing, but while querying, let's say you do the query as of latest snapshot, then you just read these two and done, right? But with merge on read, what's gonna happen is, let's say you want to query as of this commit time. Then you need to scan these log files and then also get those base files and merge the records and then produce a final result. So that is why it is called merge on read. While writing, you go ahead and simply dump your update into a log file and tell the client that commit is successful. While reading, you do merging. So there are different read and write trade-offs, and there are techniques that Hudi employs to even make this, to amortize the cost of merging. So in background, a compaction will keep on running, which you can configure compact after every 10 commits, let's say. Or you can configure it based on size. When my log file has reached a certain size limit, then go ahead and compact and produce. So what this will have, this is a new base file for the same file 1, and it has updated records. So let's say your query was coming at commit time 3, it would no longer do merging. It will directly load this snapshot. So compaction offers you a way to balance the trade-off here between reading and writing data. So that's about copy on write and merge on read table types. How does this tie up all together? So that's where central to all of this is Hudi timeline. Just like in databases, you will have a commit log. Hudi timeline is nothing but an event log. It's a source of truth for all the changes that have gone to your table, right? So a write comes along, and these are concepts specific to Hudi: file group and file slice. Very quickly, what are file groups? So you see now there is a log file at commit time 2, and whose base file is that the one at commit time 0. I'm talking before compaction, so forget compaction for now. Similarly, at commit time 1, there is a log file, and then corresponding to that base file. So the base file and the log file at commit time 1 form one file slice under the file group file 1. The base file and the log file at commit time 2 form another file slice under the file group file 1, right? So this is what we see in this diagram, that you have a file group, and within that you have file slice. So in terms of, these are nothing but multiple versions of the data. The records that have received update, you have multiple versions of the data. This kind of thing also allows Hudi to employ multi-version concurrency control in order to provide snapshot isolation between reader, writers, and even between writers. There is MVCC as well as optimistic concurrency control. But just Hudi can intelligently differentiate between a writer which is doing compaction and a writer which is doing regular insert, regular upsert, so regular ingestion basically. Yeah, so you write, and the timeline is updated. At the same time, file slice is updated. So on, you have so many file groups, and each file group has different file slices. Also, Hudi maintains some metadata. And this metadata is key to querying, which we'll look at later. Essentially, it's a bunch of indexes. And while querying, what we do is obtain the metadata. And the metadata helps the engine to filter out what file slices I don't need to scan, what data I can skip for this particular query. And then eventually it will, after let's say 100,000 files, it will eventually maybe read 1,000 files and produce your result. So that's all there is to Hudi table format on a high level. But as I said, Hudi is not just a table format. It's like a transactional storage manager, that component of the database. So what does Hudi Lakehouse platform look like, right? So everything starts with your storage. It's either an object storage or block storage, as I talked about. Then you would usually write your data in some open file format like Parquet, Avro, or Orc. And then this is the transactional database layer, which Hudi brings into the ecosystem. So what does it do? Of course, the format is there, which, the file group, file slice, timeline, and all. But then there are some background table services, cleaning older versions of data, compacting the data, clustering the data, running indexes concurrently. Even many databases today can't do concurrent indexing. Postgres does this pretty well, because that also has MVCC kind of concurrency control mechanism. So all these table services and tunable concurrency control, that's what Hudi brings to the ecosystem. And we'll see, we won't go into the concurrency control and different table services for now. We'll mainly talk about, since I'm gonna be talking about query side of things, integration with query engines. So indexes are going to be very helpful. And the concept of file group, file slice are going to be very helpful. All right, so querying data on Lakehouse. Well, so those are all the good parts about a Lakehouse. But now, what are the challenges with when you actually go ahead and deploy a Lakehouse platform? That's when everything, whatever you read in paper, whatever you read in blogs, whatever you heard in talks, those things are gonna fail. So first thing is the small file management. If you want very fast writes, what you can do is commit small batches of data, right? And you could be having, so to improve your writes, you write too many small files, but imagine from the query side, if you do a select star query, ultimately it's gonna have to scan those files. And in order to do so, it has to incur some file IO cost, right? So is there a better way that I can have 1 billion records just within 1,000 files instead of 10,000 files? So that's where Hudi automatically does this. It will compact your data as we saw. The clustering service is nothing but, suppose you have some 32 MB files, 10,000 32 MB files, and then you can tell Hudi, okay, here is my limit for the small file. I want you to stitch together all these small files and produce files, evenly sized files of, let's say, 128 MB or 256 MB. And while doing that, also sort my data by certain column. You can do that without any sort column as well, but if you know your access pattern, if you know that your data scientists, your analysts are gonna be querying by, usually in big data ecosystem, you'll see a table with thousands of columns. But if you know that only these 20, 30 columns matter more, and if I sort the data, then the query engine can efficiently skip some data. So that's about small file management. And then there is reader-writer isolation. I think that will be a separate talk, but very quickly, the timeline and the file system view. So timeline, so this diagram, right? Just remember, keep this diagram in head, that's it. So while reading, suppose some write is happening on file slice 3, right? Within the timeline, Hudi will maintain state of the commit, whether it is currently pending, in progress, or whether it has committed, whether it was aborted, failed commit. So the file system view APIs leverage the timeline and figure out, okay, as of current time, what's my latest snapshot, which file slices are committed file slices, which are still under progress. And then there are some conflict resolution mechanisms, which won't go into right now. But basically, that's how we achieve reader-writer as well as writer-writer isolation, at least between the ingestion writer and the table service writers. Between two regular ingestion writers, two or more regular ingestion writers, Hudi will ask you to provide a lock. There is no way today. We are working on that, but without providing a lock, you can't. And while writing the data, Hudi will also do deduplication. So how does it do that? So there is one thing about Hudi which differentiates it from Delta Lake or Iceberg for that matter. Hudi asks you to model your data in the sense that tell us what will be the primary key, okay? And tell us, this is not a strict constraint, at least from the upcoming release 0.14 version, this constraint of primary key will be removed. But if you configure a primary key, Hudi will maintain that uniqueness constraint. And the second field is called, which we call pre-combined field. So let's take that example of late arriving data. Suppose you had a record which was ingested yesterday. Today, somehow, due to whatever reason upstream, you are again ingesting that record. Hudi, through index lookup, it will be able to tell, okay, this key already exists, and it will, there are different payload merging strategies. Default one is simply overwrite. So it will go ahead and overwrite. If it's a duplicate record, it will just overwrite that record. You'll still have one record. You won't have two records of the same keys. But there are other merging strategies as well. And then coming to the performance itself, and that's where indexes are key. So Hudi maintains different kinds of indexes, such as Bloom index, your column stats index, and then in point 14, we are going to introduce record level indexes. We'll see how that helps. So this is the multi-modal indexing system, subsystem within Hudi. So all that is co-located with your Hudi table inside a metadata folder. And it's a Hudi merge on read table itself. We are not using any external system, any other database to maintain our metadata. It's again a Hudi table itself, but it's a merge on read table. The idea behind that was we don't want to incur a lot of latency just writing the metadata, right? So what do different, so the files index, what it will do, it will store, okay, these files are part of which partitions, and so that's about files index. Column stats is any file, what are the, you'll of course have to configure for which columns you want to build the stats, but basically min count, max count, any null count about the data. And so all these different, and record index, as it says, it's a record level index for the record key. And secondary indexes, we don't have in the current release, but they are in our roadmap. So the good thing about Hudi is you don't have to stop your ingestion. You can build indexes concurrently while your ingestion is going on. So let's come to how do you use those indexes? Fine, I'm done. I have created my index. Just like database, you can do create index while your injection is going through, and you created your index. But how does it work with query engines? As I said, Hudi is engine agnostic. So see, the main thing for query engines is it should be able to understand your metadata, whatever format you use. You'll see if anyone here, so Presto&Trino, who using Presto&Trino, right? So Presto&Trino provides a bunch of connectors, right? You'll see connectors for Hive, for Delta Lake, for Iceberg, for Hudi as well. At its core, they just need to understand this metadata. But going one level below, in order to provide efficient queries, I mean, sure, our analysts can wait 1 hour to get the query result, but they won't be happy, right? So at the, what they want is, how do you get the results as soon as possible? So quickly, Presto high-level architecture is very simple. It's your classic MPP style architecture, where you have a coordinator, which is like the brain of the system. It can get the metadata, and it can plan the queries. It can generate splits. Splits are nothing but some chunks of data, and split the workload between the workers. The workers will actually go ahead and do all the I/O stuff. They will actually go ahead and scan the files, give you the results back to the coordinator. But the key thing here is to get a better query plan, to optimize your query. Coordinator does not really, I mean, the metadata, if, assume that, very simple example, suppose you have a select ABC from some table A, where column, there is, your data is partitioned, and let's say partition column is called partition. Partition is greater than some value, right? You could very well scan the records, get the results, and then you can filter based on that. But what if at the planning stage itself, you can, you determine that, okay, I'm going to skip these partitions because they don't match my predicate criteria of the query, and then just list those partitions. So if there were 10,000 partitions, so instead of listing 10,000 partitions and then filtering, you are going to list only the, let's say, 100 partitions that match to your predicate, and then scan the files within those partitions. So this is a very simple example, but the metadata enables coordinator to do that. Your coordinator won't do that automatically, all right? So yeah, as I talked about, Presto is a distributed query engine. Well, what made Presto and Trino likable was not just its distributed architecture, but the main thing I feel were the connector SPIs. So if you go to Presto Codebase today, you will see more than 80 connectors. And the kind of APIs that they provide, it makes it very easy to write a new connector for any other data system. And it's a very highly scalable, deployed at Meta, Uber, with thousands of workers. And Hudi, so where Hudi shines is the different table formats and file system view APIs. I've linked it here, but you can, there's a link to the code actually. You can go ahead and look at what kind of APIs we have. Very fast upserts and different metadata indexes which you can employ for data skipping. So let's look at the example of data skipping. How does Hudi achieves that? So now I'm going a little bit deeper here than the high-level architecture of Presto. So within any connector, there will be a split manager. Split manager does nothing, just for any particular connector, it will try to load the splits. So the connector APIs will provide you what are the predicates. The query parsing would have been done by this point of time when you hit the split manager. You will know what are the predicates in my query. And then what Hudi split manager specifically does is, first, if there is a partition predicate in your query, it will go ahead and prune those partitions. Furthermore, if you have column stats index enabled, then the file skipping manager will, and assuming that your query has some range query, if you're doing select star, there is nothing to be, not much to be optimized there. But let's say you have some filter with range query, it will go ahead and call, so this box is all Hudi, this box is all Presto. So all these are actual class names in Presto code. So you go ahead and call Hudi's metadata reader, which will simply scan a H file. Even today, so you can get column stats within the Parquet as well, right? But you will have to pull the Parquet metadata for each of the files. What Hudi does in this index is, you have a central H file where you can get all the column stats index. And then just do range read here. This is sorted. So H file is another format which is more like a sorted key value. So this is sorted, and it can efficiently skip. At its core, it's just a binary search for the given range, and then give you what needs to be scanned. And then file skipping manager will generate splits and send it to the workers, which will read your data just for those. So this goes beyond partition pruning. Within the partition also, you have a bunch of files with column stats index. You can skip certain files within those partitions. And so this is not merged in Presto Master yet. We have a PR out, and we have benchmarked this. I'll show you quickly the benchmark numbers that we have. So we ran this for GitHub archive dataset for 6 months, which was roughly 500 million records, 220 GB. Not much for, it's not petabyte scale, but good enough to show the differences. With higher scale, you're gonna be skipping more, your skipping percentage is gonna be higher, and it will actually result in better query results. So there are different kinds of layout optimization strategies. I think Databricks by default supports Z-order. In Hudi, it's a linear sorting, but yeah, you can tune it. So without any optimization, the queries are roughly 3x slower. Queries are 3x slower, right? But with optimization, Z-order helps you where you have range queries on multiple columns, range predicates on multiple columns. But let's assume for simplicity, you have just one predicate on just one column, range predicate. So that linear sorting would help you. So yeah, the meta point being here that even you could go ahead without indexes. You'll get the correct query results, just that it would take 3x more time. With indexes, it's going to take much less time. Then there are, so that benchmark was done by us. I mean, actually, I did that benchmark. I contributed that PR. So this is a benchmark from a separate Brooklyn data company. I think Databricks maybe, yeah, this was published unknown to us. When this blog came out, it was mainly comparing Delta and Iceberg. It wasn't comparing Hudi. So we raised a pull request where we added benchmark for Hudi for the same workload. And what we found was Delta was slightly faster than Hudi. So these are different. The base data is TP-CDS data, standard TP-CDS data. And Delta was slightly faster than Hudi, while Iceberg was very, very slow. And Iceberg, so if it, so this workload is not just reading the data, it's actually loading the data and then reading, then doing some update, then reading again. So Iceberg's merge on read is more modeled like delete plus insert. It does not have any notion of key, right? So it can't go ahead and do updates just like databases do. And Delta recently has started working on deletion vector. That's pretty fast for deletes, but still not out for these. Offline, we can talk about deletion vector, pros and cons of different approaches. But high level, the point is, these three are all state-of-the-art systems, suitable for different use cases. Iceberg is very good if you don't have mutable data. All your data is append only. Iceberg is very, very good there. And especially with, if you keep HDFS out of picture, just your whole data is on object storage systems, and it is not immutable. My bad. If it is immutable, not you don't have too many updates, then Iceberg is the way to go, right? But we believe that going forward, there are going to be many, many updates. And this experience came from Uber, right? So Uber, the whole premise behind Hudi was there were tons of hundreds of terabytes of data, trips, your usual Uber trips data set. And that was, updating the data was taking quite a lot of time. So the job would run for hours. And that's when the whole concept of copy on write, merge on read. Hudi's merge on read is right from day one, right from the time when from its inception, while Delta and Iceberg are only now getting to it. So yeah, so that's from a different third-party data benchmark. Then what these benchmarks don't tell you is, when you're deploying a production system, it's not like you are just loading the data, querying it, right? Every production system has to have some updates. You can have different strategies to manage those updates. Some will lead to higher storage footprint. Some will lead to slower performance. But think from a point of view of deploying a large-scale production system. Your CRUD has, let's say, petabyte-scale data lake. This benchmark, what it does is, it actually mimics a real-world production system. So each round, you are randomly receiving between 1% to 20% of updates of the data set. And we are just comparing Delta and Hudi here. I mean, Iceberg was quite time-consuming, even for a simple workload, so we did not include it in this. What we saw with, what we observed with Delta was the time scales linearly each round. But for Hudi, these two graphs are for Hudi, these two lines. For Hudi, it stabilizes after some rounds. So these are two different versions of Hudi. In point 13, we added some more optimizations. The key thing is that the performance of Hudi does not depend on your, at least the upsert performance does not linearly depend on the data. And that is, again, because the data modeling, the little time that you as a user have spent while thinking about your data set. The only thing that we ask, that Hudi asks, is to give us a primary key, tell us which field is primary key, and tell us a pre-combine key. Or to simplify it, let's call it merge key. Pre-combine is a Hudi terminology. If you just tell us these things, that's it. We'll manage everything for you. You'd go ahead and do some your new round has 20% of updates, 80% inserts. Hudi will bucket those writes, and it will ensure that file management, small file management happens automatically, and it will just go ahead and update that particular file group. It won't rewrite the whole data. This is merge on read, by the way, not copy on write. So yeah, so the benchmarks don't mimic your real world production workload. So that's why we have to be a bit careful when you read about benchmarks. This is a comprehensive table about comparison between Hudi, Delta, and Iceberg from different systems for reading and writing. So I have specifically highlighted the Presto&Trino ones, but this is a holistic comparison, and you can read more about, so all these, you'll find the hyperlinks in this blog, which will point to official documentation, what is supported, what is not. I've mentioned the versions. So this is like the first column here after this column. So this is Hudi, this is Delta, and that's the last column is Iceberg. And actually, few things might have changed now. Delta only had Z ordering, Z order clustering for their proprietary system from database. But we as a community kind of forced them to open source it because we open source our own Z ordering, and then it's a whole different story. So we do have read support for Presto&Trino. Write support we don't have currently. It is in the roadmap, and by end of year or early next year, we should have write support as well. But what we have seen in most production systems, people are writing data using Spark or Flink. So your transactional data getting to Kafka, and then people using either Flink or Spark to do some streaming writes or batch writes. And then mostly they would be using some other system to query the data. In our experience, we have seen Presto&Trino being frequently used by other companies to query the data, but not so much to do the loading and upserting of data. So this blog will take you to a more detailed comparison. What do we have in roadmap? So first thing is we want to add support for incremental queries. So you just specify between this time range, what were the changes, just the changes that happened on the table, not the whole data, and then be able to apply those changes. Today you can already do this with Spark, but we want to add that to Presto&Trino. So everything here is for like record level index. We have it for Spark, not yet for Presto&Trino. Where does record level index helps you? So let's say you have keyed updates or deletes. Your record key field was some ID, some customer ID, and you want to go ahead and delete the data for that customer ID. Then if you maintain a record level index, Hudi will directly tell you, okay, this is the file these are the files which contain this customer ID. Go ahead and delete it. That's it. So that's all that index does, nothing else. And then we are also working on building new merge algorithm, how to efficiently merge the data, and new APIs, which makes it easier for anyone to integrate with other queries, not just Presto&Trino, but we have been in talks with a community of Star Rocks. That's another community in China, so they are also building a system and integrating with Hudi. So yeah, these are more at the abstraction level. And then another feature that we are working on is multi-table transactions. How do you take that example of customer ID itself? How do you go ahead and suppose you want to delete the record for that customer ID across multiple tables? How do you atomically do that? So there is an RFC out for there. You can review it and comment on it. There is an RFC for Hudi 1.x that has a lot of exciting features for support for unstructured data as well directly. Right now, Hudi is still under the hood. It's either a Parquet, Avro, or H file. So, but we are exploring ways of directly processing unstructured data. So yeah, that's all in our roadmap, and a little bit into what. So I work for Onehouse, and we are again working on an open source project in union with Microsoft. And what we are working at, just a glimpse into that, one of the projects that we are working at. So there was a big announcement. Anybody who has been following Lakehouse, Databricks, then during Data AI Summit, there was a big announcement for Delta Uniform. Essentially, it's how to build an interoperable lake. I mean, you write Hudi format, your Databricks engine should also be able to read that. So what Delta Uniform is trying to do is make, like you still have to ingest in Delta, and then it can be interoperable. But we are attempting this interoperability. We call it omnidirectional interoperability. Like, fine, go ahead, load your data in whatever you want to do, right? At the end of the day, our belief is that what matters more is not the ETL operation themselves, but the services that are accompanying that, the compaction, the clustering, the indexing part, those matter more. So yeah, that's it I had for the talk. I have just linked all the resources in one slide here about Hudi-Presto&Trino design and some other things that I talked about earlier, the blogs. Our community has been growing leaps and bounds since 2020, and a lot of companies, big companies, mid-stage companies have been using Hudi. Our PMC, so Apache Software Foundation has this PMC and committership thing. So it's a pretty diverse committee, Apache Hudi, people from different companies, not just one company contributing to Hudi, engaging with Hudi. And yeah, if you want to join, engage with our community, give us a GitHub star, come join us on Slack, come to our weekly office hours where we discuss more stuff, troubleshoot some issues live, and that's it I had. Yeah, any questions? I'm happy to answer. Yes, sir. That's pager duty alarm. Huh?
Yeah, so when it comes to the data lakehouse architecture, so we have both OLTP and OLAP data ones. And what is the overhead if I use Hudi, right, in a data lakehouse for the both OLTP and OLAP? So that's what I wanted to hear from you.
Okay, sure. So overhead in terms of storage?
It's not in terms of the storage. Hudi is good in terms of the querying, right? My OLAP data. It has indexing and partitioning, acid compliance and salt, which we talks about it, right? Where I'm looking more into the OLTP.
Okay, yeah. So OLTP databases, one thing is there that they will have a commit log, right? And there are other systems. Hudi doesn't directly consume from, let's say, Postgres' log, but there are systems like Debezium, which will consume those logs. And then through Debezium, we can consume CDC events for the changes happening on your OLTP databases in near real time. I'm again using the word near real time, which, I mean, you can't have, can't think of some sub-second latency in this pipeline. Yeah, so Hudi is able to consume from the event, CDC events being generated by Debezium, and then write that to wherever you want to. Your sync could be anything. Most commonly, people will just write it to an object storage system. And like medallion architecture is very common. First, you will just consume those CDC events and write a bronze layer, raw data, and then do some processing to produce the silver layer. Because CDC events will have some metadata of their own. Debezium will add its own metadata on top of what Postgres is adding. So people have to do that processing a bit. In terms of overhead, so as I said, like if you have your raw layer maybe raw layer is just immutable. So Hudi has this concept of write operation types, different types. So we differentiate between, let's say, usual insert and bulk insert. So in case of usual insert, we will do pre-combining or deduping on the fly within the batch of records that is coming in. We will do index lookup to figure out where the record is going in. But in case of bulk insert, we'll simply, it's very simple, plain Parquet file writes, let's say. So we don't do all that stuff. So if you know, that's the thing. You have to know that this particular layer is immutable. You're just adding records to it. You're not updating. Then you can use bulk insert operation, or else use upsert operation. Upsert operation will provide you deduping, pre-combining, and very fast upserts, but at the cost of some extra storage overhead. And I think compute overhead won't be much, because through index lookup, we clearly eliminate. So we'll figure out, okay, there is an invariant. If I can go into a little bit of implementation detail, there is a powerful invariant in Hudi. A record key can only go to a particular file ID, file group thing that we talked about. So there is one-to-one mapping between record key and file group. And that's what the Bloom index tells us. Worst case, Bloom index is also probabilistic data structure, but very space efficient. And you can tune the error rates for the Bloom index. But for most use cases, 99.99% of use cases where you have mutable data, upsert is very, very fast. If you have immutable data, then change your operation type, make it bulk insert.
Okay, so it means like when I go for immutable data, so you're saying it right, not use the Hudi because the dynamic schemas is getting changing, or else, let me ask you in this way, right? The operational cost in terms of the compute and the storage which I'm looking at, and why I'm asking it to my GenAI integrations.
Sorry, which integration?
With GenAI.
Okay, GenAI.
Okay, to do those integrations, right? Do I need to use Hudi for querying my data with the help of the fast APIs and keep cognitive services, right, for searching the data? Can I use both the combination? Because Hudi is powerful in OLAP, right?
Yeah.
And it has a limitation for the couple of tools, but it's powerful, right? It's proven it, right? The query, the bigger size of the query, it's going to give you the one. But when in terms of like you are combining the Lakehouse architecture, because that's where we are heading in a future, like one big Lakehouse for the entire organization, and we'll have this both the OLAP and OLTP and domain-driven architecture on top of the microservices of the APIs, right? And followed by our GenAI indexing. So how you are gonna give me the architectural rights? Do I need to go in this way? Or you said like, okay, let's use Hudi itself, right? Because it's again open source, right? What your thoughts?
See, I think my opinion, table format is very small piece of the whole ecosystem. It's a very small piece, right? When it comes to managing the whole Lakehouse, the things, there can be debate about, okay, this table format has lesser metadata and storage footprint is lesser, while Hudi maintains some extra metadata. But we need to think from the perspective of what do we get from those extra metadata. So anyone who has used Hudi here will know that Hudi will record some metadata columns with the data itself, _Hudi _ columns, right? So they help us in certain way. If I have to summarize in one sentence, like if you have immutable workload, then go ahead and use Iceberg. I'm not even comparing with Delta. Iceberg is real state of the art for immutable workloads, and it will have minimal footprint. storage footprint, and works like a charm for immutable workloads. But if you have a mutable workload, then you go with here again I'll categorize. If you only have deletes in your mutation, let's say all you cared about is everything is immutable, but due to GDPR regulations, I need to update my data for delete some records, then Delta Lake is pretty good with their deletion vector approach. I think they have made deletes very, very fast. But when it comes to updates, then Hudi outshines both of these. Because Hudi does not treat updates as delete plus insert. Hudi, those extra metadata, the Bloom index, the extra meta columns in the record itself, they help us Hudi to figure out efficiently, okay, what is this record key belongs to which file ID, and within that file as well, what block needs to be updated, right? We are not going to rewrite the whole file as is. There could be some bigger files as well, right? So why rewrite the whole thing if we can just update one particular block? So those are the things. But I would say the main thing is the interoperable format that I talked about. Format is very thin layer, so people should be able to write and read in any format. What matters is who manages the other things better. All these systems, Delta, Iceberg, Hudi, they maintain multiple versions of data. But if you don't clean up your data, you're ultimately, fine, storage is cheap, but it's not free, right? You are going to pay some cost to S3, right? So who can manage this without, I mean, I just said 2 or 3 configs, and something goes ahead and cleans my data in the background without really affecting ingestion. Something goes ahead and compacts my data in the background without really blocking ingestion. So those things of Lakehouse architecture will matter more going forward.
Okay, so that's actually brought me the one more thing. So when you're comparing Hudi on-prem and cloud, I'm considering the both, right?
Okay.
So I can use Snowflakes and the ones. Even I can use Azure Data Factory, Azure Databricks itself, right? So that's also gonna gives me the Delta Lake ones. How you are going to say like Hudi is best both on-prem and cloud when you have the hybrid cloud solution?
So Hudi started with an on-prem solution. It wasn't built for the cloud from day one. Uber had huge HDFS cluster on-prem, right? And it was built for block storage. So sometime in around late 2019, 2020, we started adding, internally Hudi maintains a wrapper file system on top of the file system, underlying file system implementation. And so we started to optimize for cloud workloads. If you're more familiar with the difference between HDFS and object storage systems, the block and object storage system, some operations are not atomic on S3 or other object storage systems. So Hudi takes care of that. But to your question, sir, that how would you say Hudi is the best? So Hudi, again, I'm not saying Hudi is the best everywhere. It's the state of the art in the use cases which we see companies have been moving more towards. Very few companies like Uber were doing mutable workloads back in 2016, 2017. That time even, I think data lake was also not that prevalent. Warehouses still do a bunch of things which they are pretty good at. And Snowflake is a big company, not for nothing, right? So they were the ones for big data world, they were the ones who started with decoupled storage compute. And even today their architecture is pretty solid. But you go ahead, you must have read about the blog, if you are in this ecosystem, you have read about the blog about Iceberg and Snowflake. We actually tried that. So Snowflake has external table integration with Iceberg, and that just sucks. Yeah. So what we are doing is, at the end of the day, Delta has some metadata, right? Some protocol, right? What if Hudi, the different components in Hudi can understand that protocol? So we are moving more towards that. We don't care whether you use Delta or Hudi. Go ahead, ingest in anything that you want to. But we feel with the how we try to be ahead of the game is by having these different indexes and table services, and that too asynchronous table services. You go ahead and try to vacuum or optimize in Delta, right? You will hit into issues with if your ingestion is also going on at the same time. But Hudi is able to resolve those conflicts. So those are the things that we are building towards, and we hope the community will also like it. At least Hudi community loves it, but the larger data engineering community will also love it. Yeah, sure.
Thank you so much, Sagar, for the insightful talk.